What can we conclude more or less about special relativity? Well, here's just a quick rundown. Special relativity conclusions are based wholly on the constant speed of light, and the variability of mass and distance and the relativity of time, specifically the relativity of time. That's where they're going to get their time dilation notion, right? The idea, theory. If there's no such thing as time, if time is a concept, then time does not exist. Only objects can be said to exist in physics. You cannot say that a concept exists in physics. If you don't like the definition of exist, object that has location, you want to have a concept that has location or concept whatever, you define the word exist, and then we'll know what you mean by exist. Define in such a way that you can not only defend it, but that you can use it consistently. Okay? And special relativity suffers a sudden death without time. Okay? Time is not a thing, so it cannot flow or move. Time has no direction, right? Direction is a qualitative concept and has no business in math. You cannot put direction in an equation. What are you going to put for direction in an equation? You can put a number, you can put a variable, you can't put direction. Okay? And direction belongs exclusively to physics. Father Universe, what I'm going to talk about next, recognizes no such notion as time. And that's the one that's going to defeat special relativity completely. Okay? Just get rid of it completely. Time is an invention of living entities. Okay? So let's go with that, the last two there. Let's show why you can't use the word time, not only in physics, but, if you can't use it in special relativity to make your case in special relativity, it's the end of special relativity. All the measurements that they made, all the theories that came out of that, all the conclusions, down the drain, down into the trash can where they belong. The ash heap of history. Okay, so what is this? Let's start with time dilation. Okay, the equation, here it is. This is just quickly through there. We're not going to do any math here. We just want you to understand the concept for those of you who are not familiar with it. You have time of the observer, guy looking from afar usually, right? That's the way they present it. And you have a passenger. It could be on a train. It could be on a rocket. We don't care. But there's a passenger traveling close to the speed of light. So you have that velocity of the passenger right at the bottom there over the velocity of light. That's equation number one. Let's do it with some numbers real quick so you can understand how this all came about. If you're traveling at 99% of the speed of light, which is equation number two there, well, you're approaching the speed of light, which would be equation number three, right? You're almost c squared over c squared, and that's 1. 1 minus 1 is 0. Time divided by 0, guess what? Undefined, infinity, etc., right? Or the laws of physics break down at the singularity, whatever term you want to accept, okay? So the law of physics broke down because, you traveled at the speed of light. And that gave them an idea that nothing can travel at the speed of light, either at the speed of light or faster. That's the only one they got right, but they don't know why. Again, physically, we do it with a rope, no problem. Okay, so that's where we start. That's the equation, right? Okay, so where do we go from here? Okay, one of the things they tell you based on this equation, one of the conclusions they get is that if you're up there in outer space, time runs very slowly, whereas you're close to the if you're close to the center of the earth, time runs very fast. They said gravitational effects make time run faster. So if you were on top of Mount Everest, or even in a building, they said, like if you're at the Empire State Building and you're at top of the building, at the bottom of the building, the guy at the bottom of the building, time is going to run very fast and time at the top is running slow. That's what they tell you, okay? And everybody just accepts and say, yeah, okay, so they proved it mathematically, etc. And no, it's absolute nonsense. So that's the first notion that we want to tear apart. Okay, here it is. Here's Einstein and his cesium clock, his atomic clock. And he puts it at the bottom of the Eiffel Tower and the top of the Eiffel Tower. And he says the clock at the top runs fast. The one closer to the Earth has to be running slowly. My point here is that we don't need an atomic clock to measure the speed of time, right? One way or the other. We can do it with an hourglass. If you have an hourglass up there in outer space, it's going to go very slowly, and the one close to the Earth is going to run very fast because it's closer to the source of gravity, which is the center of the Earth. So if you have one at ground level, that clock should, this clock, here it is, okay? This one should run fast, okay, if you're in close here to the Earth than if you were out in outer space. In outer space, because gravity is less, right, this should run slower, okay? And that's essentially the opposite of what Einstein said, okay? Sometimes I get these confused, okay? But that's one issue, okay? And another issue is the famous twin paradox. You have one twin leaves the Earth, right, and the other twin stays behind. And this is more or less what they're referring to. Let me illustrate that for you here. Okay, here it is. Okay, you have one twin, and he's going to leave the Earth with his rocket. He's going to go to a black hole, turn the corner, right, and come back. Okay? And so the question is, is time the same thing on the rocket that it is on Earth? That's the issue that they're trying to answer. Is that what happens? Is the time the same or is it changes? And they say the time is different for the guy who's traveling, okay? But they reach the conclusion because of that the guy on Earth did not age. He aged a lot, whereas the guy who traveled did not age hardly at all because he's traveling close to the speed of light. And this is the way they illustrate it. Okay, here it is. The illustrations are mine, by the way, but I try to illustrate what they're trying to say as best as possible. Okay, and here it is. Okay, so we have this fellow. He's going out, and you can see the clock running fast. Okay, and the guy who's traveling, his clock is running slow, and so he ages very slowly. The guy on Earth, his clock is running very fast. He's aging, I guess, faster than the guy who travels. Okay, that's the issue. So he might be 40, 50 years older than the guy who traveled. That's essentially what they're saying. Okay, and so how do we answer this? Well, one way to defeat that, we already looked at the hourglass being on top of Mount Everest or the Eiffel Tower being slower than the guy at the bottom. That's one issue. The other one is, you can do this experiment of the traveling twin and just imagine they take a rope, okay, a long rope, and you put knots on the rope, okay? And between any two knots, you have the distance that Earth travels in 1 year, okay? So between two knots, we have the distance the Earth travels in 1 year, and you count all these knots. Let's say you went 10 years outwards, came back 10 years. So that's, 20 years, right? Hopefully, when you arrive back, you both aged the same amount of time because the same amount of time passed between both of you. You don't carry an atomic clock because they're notoriously inaccurate at different distances and at different temperatures. Here we have knots, right? That's very straightforward. You have a knot that is I think it's 940 million kilometers from the other knot. So you have all these knots, and they're all, over here. There it is. We have all these knots, and one knot's here, the other knot's here, right? Between them, you have the distance of that the Earth travels in 1 year, which is the standard for the year, which is the definition of a year. Here's the definition of a year, right? Looks more or less like that. The Earth travels around the sun, and once it goes one full revolution, that's what we call 1 year. And so that hasn't changed ever. We still have a year being measured by the rotation of the Earth around the sun. So if you want to know how old anyone is, I don't care how far he traveled. I don't care how fast he traveled. I don't care if he went to the other universe through a wormhole and came back. When he comes back, we just need to count how many times the Earth went around the sun, because that's the definition of the word year. Okay, and again, the other way you can do this is, measuring the with knots. That's objective. Knots do not dilate. Okay, and here it is. You can see the rockets going, and we're going to take this road. We're going to count, how many knots we had, okay? And hopefully you got 10 going out, 10 coming back in, if you release the knot from your ship as you're flying, right? It should be straightforward. We should be able to count to 10. And I hope the mathematicians can count to 10. And so, if you do it this way, the times the Earth went around the sun has to be the same as the number of knots, which would be 10 going out, 10 coming back. That's 20 years. They both, the two twins should have aged both 20 years. Period. We're done. There shouldn't be any question about this, because this is straightforward math. And if they can't do math as simple as this, well, I don't know. Okay, but there's a more fundamental reason for why special relativity dies a sudden death. Father Universe does not recognize time. He has no idea what time is. We humans, or other living entities, we're all aware of time. Even a lion is aware of time in a very rudimentary manner. He looks at the wildebeest or the zebra, right? And he already has a notion of how fast they run, so he gets up close, the lion gets up close, looks at the zebra, and knows at what point he can start running and trying to catch that zebra, right? And so, if another lion is watching the whole scene, he's seen the lion when he was hiding, and he saw the lion when he caught the zebra. So he's got a notion of time. He's got a sense of time. He has that before and after. He's got the starting point and the ending point. So even though he can't do calculations or whatever, he's got this notion of time, this rudimentary notion of time. So to say that animals don't have time, yeah, they do have time. Even the lions, I guess, always wait for for this great cycle of the movement of many animals, right, that they're going to hunt. They know when it's the season to be jolly, because the herds come back close to where the lions are. They know that's the time of the year to go hunting. So they have a sense of calendar of time. They have a little sense of that. That's my take on that. But what's the issue? The issue is that Father Universe does not recognize time. So let's look at that. Time dies with Father Universe. There's no such thing as time. And here you have the Universal movie. Okay, what is that? Well, this is a movie of the universe. In one frame, in a single frame, you only have static concepts, okay? You have only every atom in the universe, right, at a given location with respect to all others, okay? So there's a distance between every atom in the universe at any given point in time, so that in a single frame, you have no motion whatsoever. If you want to see motion, you need to roll the movie. But it turns out that, Father Universe does not do that. He can't do that. Father Universe always looks at himself, and that's what he sees. So if God were to take his camera and take a picture of the universe, you could think of it as a three-dimensional movie. That's why I put the projection there. But what you're talking about, every atom in the universe, right? It's at a given location at a given distance from all others. So this is Father Universe, only one frame. Father Universe does not recognize motion. He goes to sleep for another 1,000,000 years, then he wakes up, every atom is at a new location. Okay, and that 1,000,000 years is a split second. Like they say, it's God's time, so to speak. Okay, yeah, there's only a single frame. Okay, and so when we look at something like, they talk about an event in special relativity, where this event happens at a certain time, but the observers at different distances, at different locations, they don't measure the event simultaneously. So it's this notion of simultaneity that drew us into special relativity that they emphasize. And so let's look at an example here. We have this is the first frame in our movie. We have two observers. Okay, and there's going to be an event that happens, supernova. The frame in which it happened, 632. But neither observer has yet seen the event happen because they're too far away. So the event, you can say, takes up more than one frame, but that's not what we're talking about. We're saying the moment the explosion happened, the exact frame of the movie, if you were to take a snapshot just when it's about to burst, That's the frame that we're looking at there, okay? Okay, so what happens next? Well, the beam travels, and still neither observer has seen the beam. In frame number 634 now, what we have is one observer, the one closest to the event, sees it for the first time. But the observer number 2 has not seen it at all. Next frame, the second observer still has not seen it, even in frame 635. Finally, the observer sees it. Light reaches his eyes. This is more or less what special relativity talks about, the fact that different observers see different things, measure different things. Now, as you can see, it hasn't changed the frame 632 in which the event happened. You can say if you take a snapshot of what's about to happen, that happening, in fact, you could take frame 632 and 633 also, and you can say it happened in those two frames and still no one saw it. Neither of the two observers saw what happened, okay? But actually, Father Universe only exists in a single frame. So as far as Father Universe is concerned, all the atoms in the universe at a given location. Frame 632 represents the simultaneity of the occurrence of the event, which is not really an event. It's just a snapshot of a given point in the event. Turns out that I did this completely wrong. Why? Because I'm misrepresenting Father Universe. Let's represent him the proper way so that we can understand what's going on here, okay? Here's again, frame 631, nothing's happening. We see two observers. Okay, what happens next? Well, what happens next is there's a supernova, right? But it's in a single frame. See, we don't have all the frames of the movie because Father Universe doesn't recognize the entire movie. Father Universe does not recognize this. That's not what he sees, okay? As far as Father Universe is concerned, he's not in many frames at the same time. He doesn't have atoms in every location that we had in several frames of the movie. No, he only recognizes one frame, and that's that one. That's the only one he recognizes. So when the light is still traveling, like to the two observers, and none of them yet see it, that's all Father Universe experiences. Every atom in the universe at a given location. There is no movie as far as he's concerned. Movie is an observer-related issue, right? Idea or notion. And here the first observer sees it, the other one doesn't see it, okay? And again, what you're seeing is that, certain things happen in certain frames of the movie, and what each person measures, here he doesn't see it, and here he does see it, okay? What all these people are doing, they're measuring, and measurement has nothing to do with what is. The fact that someone measures something a little later than the other guy has nothing to do when the event actually happened. And that's where people get confused. They say, well, did the event happen at a given time or not? And it did happen in this, you could say, universal time, which is just location, okay? In that frame of the movie, it happened then, okay? That's when it happened. When people measure and what they measure, that's subjective. That depends on how much distance they have, how fast the light is, etc. It depends on something totally different, but it has nothing to do with when the event happened. You can't change that. And one of the issues there is that, again, you can't go back in time because there is no frame of the movie, no atoms in that frame of the movie that you still remember in your brain. That one doesn't exist anymore. Those atoms are now somewhere else in the universe. So you cannot go back in time with a warp drive, with a wormhole, with a tachyon, writing a tachyon. You can't go back in time because there's no place to land. Okay, there is no frame of the movie called the past. Okay, it's not there. All the atoms have moved to a new location in the entire universe. And again, if God takes a picture of every atom in the universe, a 3D picture, and shows it to you, you would see just every atom in the universe at a distance from all others. And there is no other picture. He can show you the picture, but there's nothing to land there because those atoms are no longer there. And that's the problem with time travel. In fact, the Universal movie destroys actually the entire language of mathematics, of mathematical physics. Why? Because here you see that these people say that mathematics is the language of physics, right? And that's only if you're looking at a movie. Then you can use the word time, you can use the word energy, and all these motion words, okay? What does Father Universe recognize? He only recognizes a single frame of the film. And all you have there is illustration. You have objects, static concepts. Okay, that's all you have in one frame of the movie. And so this notion that the mathematicians have developed that you can have all these words such as time and things that involve motion, such as energy and mass, that's us. That's us humans. We invented all these concepts. In fact, all concepts have been invented by man. And Father Universe only recognizes static concepts like object, like, distance, location, existence. That's what Father Universe is, because that's all, that only shows the atoms at a given location with respect to all others. Can we figure out what this universe is? Very easily, and I showed this the other day. You have let's do it this way. You had the two atoms bound by a rope. This is the basic system. Two atoms bound by a rope. Multiply this by a very precise number such as gazillion, and that's the entire universe. That's the entire matter of the universe. Atoms bound by ropes, all interconnected across the universe. What serves as a backdrop to that? Nothing. We use the word space or vacuum to refer to that nothingness. So we have this nothingness, which is that which has no shape, and we have the somethings, all these atoms bound by ropes all across the universe. And that's the something. We have the something and the nothing, and that's the definition of the word universe.